Good evening, everyone, and thanks for coming here. I know it's Friday evening, and we really appreciate you guys taking time to come here and watch this event. So, my name is Rishabh, and over there is my friend Sarah, and we are members of the ANU Optica and SPI student chapter. And we would like to thank you for participating with us for this public talk on the occasion of National Science Week, How to Watch Netflix on the Moon. So before we start, I would like to pay my respect to the traditional owners and custodians of this land, the Nagunawal and Nangabari people. And I would like to extend my respect to the elders past and present. So I think many of us may have heard about the Artemis II mission and the critical role Australia, especially ANU, played in supporting the ground optical communications. But most of us don't know what's the groundwork that has been gone in laying the foundation for all of this. But don't you worry. Today we have two great speakers here, Cameron and Jackie from Research School of Astronomy and Astrophysics, and they will tell us more about the things and the work that goes behind the curtain. So without further ado, I would like to give the mic to Jackie and Cameron.
Take it away.
All right. Can you hear me all right? Cool. Rightio. G'day, everyone. My name is Jackie.
And I'm Cameron.
And we are PhD students from the Research School of Astronomy and Astrophysics, here today to talk to you about how you can watch Netflix from the moon. So I'm going to start today's talk with an all too familiar feeling. You're on the moon and you're trying to watch Netflix. And, you know, the quality of the connection is just absolute rubbish. It's lagging, it's buffering, the resolution is dropping. And you think to yourself, man, why don't we have good enough internet on the moon to watch my shows in 2026? I'm sure this is a common problem for all of us. Well, today I'm going to be talking about how we're developing optical communications to speed things up a little bit for internet in space, and how the very talented team of engineers up at Mount Stromlo supported the Artemis II mission earlier this year to do just that. So before I get started today, I will make it very clear that Cameron and I supported the mission. The real magic came from all the insanely talented team up there at Mount Stromlo. All right, let's get into things. Oh, here we go. Sweet. Okay, so in case you don't follow space news religiously, the Artemis II mission took place earlier this year. And this was a mission by NASA to send people back to the proximity of the moon. So this was a 10-day mission that saw a crew of 4 astronauts launch from Earth, fly around the moon, and then come back. So it's interesting to note that this is the first time that humans have been even anywhere near the moon, let alone past low Earth orbit, since 1972. So it's been quite a while. So the goal of Artemis II, in a large way, was a stress test for both the systems and the crew. Turns out, since the 70s, technology has evolved quite rapidly, and we have a couple more safety procedures in place than back in the space race. So the idea was to make sure that all the hardware is working, all the ground crew's on the same page, all the astronauts are on the same page, for when we actually do the real deal and land on the moon on Artemis IV. Okay. So here's the flight path of the Artemis mission itself. Artemis, the Orion capsule the astronauts were in, highlighted in pink. So the idea was to get into an elliptical orbit around the Earth and then enter what's known as a translunar injection orbit, which basically just means using a bit of the Earth's gravity as well as a fuel burn to go around the moon and then slingshot straight back. So it's important to note that, yeah, they didn't land on the moon, they just went around it. And basically the whole thing went off without a hitch. If you don't count a couple of issues with the toilet on board and the Microsoft Authenticator app, everything went perfectly according to plan. So to set the scene on how we relate to this, I'm going to introduce laser or optical communications. So when we talk about wireless communications, we're typically thinking about what our phone uses, which is radio frequency. This uses a wavelength of light that is invisible to the human eye, but can very helpfully penetrate through thin objects. So this is how, your phones work, basically anything wireless works, your Wi-Fi, all that. And whilst it's a very useful kind of technology, It's certainly showing its age in the modern era. So as more and more people get connected to the internet worldwide, radio frequency infrastructure just can't quite keep up with the demand globally. So to remediate this, we've been developing free space optical communications, which, yes, use near-infrared lasers to send the same information at a much faster data rate. So this technology has been in development for quite a while. It's been in development specifically for fiber optics, which use special cables that guide the light on its intended path. And our challenge is taking this light out of the fiber and putting it into free space. Turns out it's pretty hard to run a fiber optic cable to a satellite or anything, a capsule going around the moon. And so it looks like free space optical communications is the way to go for that one. Okay, so to motivate why we're actually working on this technology, you have critical infrastructure in Earth's orbit, such as space telescopes. There's the Hubble Space Telescope and the James Webb Space Telescope. These are both very important telescopes that make observations of astronomy in space. And the issue with especially the James Webb Space Telescope is that it generates so much data, we can't send it back to Earth quick enough. So on the radio frequency link that the James Webb Space Telescope currently uses, it takes over 5 hours to downlink all of the data from the hard drive back to Earth. This actually is not as fast as it's generating data, which means you actually have to throw out a lot of the data before you even get it back to Earth, which is very unfortunate. Now, with a modest optical connection, you'd be able to downlink the same hard drive in less than 9 minutes. That means you don't have to throw out any data, and you can get to processing your data much, much quicker. NASA has also had a keen interest in lunar exploration in the past few decades, eventually aiming at establishing a permanent human presence on the moon in the form of a moon base, if you will. And if you have a whole lunar colony with a bunch of scientific instruments, you've got individuals with bandwidth needs, the only way to service all of this bandwidth is using an optical connection. Radio frequency is just not going to cut it. You then have the internet and telecommunications industries. These have already been revolutionized by free space optical communications. You might have heard of Starlink, for instance, which provides internet coverage worldwide by using optical inter-satellite links in space before changing to radio frequency, where they service the ground layer. And then you've also got security and cryptography applications. So in defense right now, a super interesting topic they're looking into is a very secure way of communicating known as quantum key distribution. And this is a technology that can only be made possible through lasers. Doing this over large distances also requires you to involve a satellite into the equation, but we'll talk more about that later. Okay, so wrapping back around to Artemis. Artemis was equipped with an optical communications terminal, specifically a mascot type terminal. So this is an optical terminal that's had heritage. It's been tested on the International Space Station. It's had extensive testing on the ground segment as well. And it was able to support a maximum data rate of about 260 megabits per second. For reference, doing a radio frequency link to the moon might get you about 10 megabits per second, so a lot faster than that. So the point of including the optical payload on Artemis II was for a demonstration of a high-definition video stream that would be streamed back to Earth. And this was streamed on YouTube. If you ever tuned in on the YouTube link to the actual camera footage from outside the Orion capsule, if it was in nice crisp HD, that was us. So I have a bit of a demonstration. You've got the resolution afforded through radio frequency versus optical. You can see the image quality immediately get better when you switch over to optical. The reason for this is because you can send a lot more data over an optical link per second. In terms of a video stream, this means more pixels, higher definition, even higher frame rates if that's what you're aiming for. And so optical communications is the only reason we were able to do high definition video streaming all the way out from the moon back to the Earth. I'll let that play out one more time. Okay, so over to our work here at ANU. The Mount Stromlo campus, about a 20-minute drive away, is home to the Quantum Optical Ground Station, or QOGS. And this is a building that is purpose-built for laser communications from the ground up. We've had a lot of exciting projects recently. We've been supporting industry, we've been supporting research, we've got a couple of defense projects going as well. And so, yeah, doing laser comms in this kind of emerging era is really exciting stuff. We've also been scoping out use of the Anglo-Australian telescope, which is up at Siding Spring Observatory, which is about a 6.5-hour drive north near Coonabarabran. And this telescope is, currently being scoped out for deep space optical communications. So that's when we want to go doing optical communications a lot further than the moon. All right, so in terms of the reliability of an optical link, we're pretty lucky. It's basically a straight shot if you're trying to talk to a satellite with a laser link. Thankfully, there's no kind of physical object that manifests in the sky and blocks the link. You know, there's nothing that's going to cause a severance in the... Oh no. It appears a cloud has disrupted our optical link. So when a cloud blocks the light, it's not like radio frequency. It can't just permeate through the cloud. Optical is as it sounds, optical. When an object is in the way, you've got no connection. And it doesn't even have to be a cloud. Honestly, it can be mist, fog, rain, literally wind can cause issues in disruptions with an optical link. And so, in that way, the cloud is very much the natural predator of the optical engineer trying to do an optical link. So, you've tried to do a link and a cloud has rolled through. What are we going to do? We're going to give up? No, we're winners. So for the Artemis mission, we actually thought about this. The optical payload was serviced by 3 distinct optical ground stations. There were 2 in the United States, 1 in White Sands, New Mexico, and 1 in Table Mountain in California. We then also had Quantum Optical Ground Station here in Canberra that serviced the third part of the link. And so when a cloud rolls through on one ground station, because all of these places have decorrelated weather patterns, we can simply hand over to another ground station. And that's exactly what happened. We had instances where we had an active optical link with one of the ground stations, and we could just hand over to another one. And it worked basically completely fine, which was really good to see. So another reason that motivates having site diversity with your ground stations is uptime. So this plot demonstrates when the 3 optical ground stations would be able to see, in this case, the sun at any given time. And so if we use this as a proxy for the Orion capsule, which the optical ground stations were actually tracking, we can see in the red highlighted section that having a ground station in Canberra significantly increases the uptime of the optical link. So the eventual plan is to have ground stations all around the world. This way, you can always have somewhere on the planet that's tracking the object that you want to look at, and you can keep your uptime to be 24/7. All right, and it appears a cloud is blocking me, so I'm going to hand over to Cameron, and he's going to talk a little bit about the system design.
All right. So now that Jackie's told you a bit of the why, I'm going to start to talk about the how. Now, every element in this system is built around 2 questions. The first question is, how do we turn the internet into light? And the second is, how do we turn that light back into internet? So everything we're doing is around these 2 questions. And I've got a system diagram here. And that first question is all wrapped up in the Orion capsule, where they've got that mascot terminal that Jackie was talking about. If you want to know how to turn the internet into light, you're going to have to ask NASA, because we worked on the downlink. But in broad strokes, the way our system worked, the Orion space capsule points their laser at us in Canberra, and we catch the light with our telescope. From there, we route the light down into our detectors, and from our detectors, they turn the light into electricity. Then that electricity gets pumped into our modem, and that modem can turn the electricity into internet, where we can shoot it out into the World Wide Web. So the first system I'm going to talk about is the telescope we used. So this was a instrument from a company named Planewave Instruments. It's a regular-ish astronomy telescope with a 70 centimeter aperture, so that's about this big. And this was designed in collaboration with NASA specifically for free space optical communications applications, so for missions like this. But fundamentally, it was just a regular astronomy telescope. And you can see some of the cool pictures we took in its off time, where you can see the rings of Saturn, the clouds on Jupiter, and you can even read the tail of a spacecraft. Sorry, aircraft. Don't worry, we turned the lasers off when we took this photo. Now, the reason we have such a big telescope, not big by our standards, not by astronomy, is because the Orion space capsule's about 400,000 kilometers away when it transmits out of its 10 centimeter aperture. So as the laser beam's propagated through all that distance, the beam's going to expand, and as it expands, the power gets diluted, it gets weaker. So we want a big telescope to just catch as much of that light as possible. Then in the same way, you can bring a magnifying glass to a focus and you can burn ants or whatever you're doing with it. You can bring your telescope to a focus. And in our case, we brought that focus onto an optic fiber. So we bring the telescope into focus on our multi-mode fiber. We cram all that laser into an optic fiber, and then we can route that optic fiber downstairs to the rest of our system. So the lasers come in, hit our telescope where we've caught the light, and we cram it into an optic fiber down to our detectors. And the detectors in question that we use are superconducting nanowire single photon detectors, which is an absolute mouthful. But fundamentally what this is an instrument which can measure the arrival time of photons with a remarkable precision. We're talking about picosecond accuracy on the smallest fragments of light possible. Now, the way this system works is we take a nanowire, small wire, and we arrange it in this zigzaggy pattern. Now, these wires are 70 nanometers apart, so that's smaller than the wavelength of the light we are looking at. And then we cool the wires down to about 2.5 degrees above absolute zero, so minus 270 Celsius-ish, at which point the wire becomes superconducting. Its resistance drops down to zero, and the electrons can pass through completely uninhibited. They don't slow down at all when they go through the wire. Now, we actually tune the temperature so it's just on the edge of this superconductingness. So if it heats up just a little bit, suddenly that superconducting is going to break and the electrons are going to slow down. So when we plug that optic fiber in from before, the photons are going to start hitting the wire. Every time a photon hits the wire absorbs the photon, and it warms up just a little bit. This causes superconducting to break, which causes the electrons to slow down, which causes a voltage spike. Then we can measure the timing of that spike with very high precision, with picosecond accuracy. And we can use that to figure out the arrival time of each of these tiny pulses of light. Now, the reason this is important for us is because unlike in astronomy, where they're taking photos, they don't really care about when the photons arrive, they just care about how many there are. We're doing communications, so we need to know exactly when each pulse of light arrives so that we can decode it into a communication signal. So, to recap again, we've caught the light in our telescope, crammed it into an optic fiber, sent that optic fiber to a detector, and that detector converts our light into electricity. This still isn't internet though. If you try and plug this into the wall, nothing's going to happen. So we need a modem to turn our random electrical signal into internet. And here is where I can talk about the encoding mechanism we used. So if we think about the internet, computers, it's all ones and zeros, right? So your first instinct for how do we turn a laser into the internet might be, okay, what if we turn the laser on for a 1 and off for a 0? So this encoding scheme is called on-off keying, and it works, but in reality, your electrical signal is never going to look this neat. It's probably going to look something like this. Sometimes it's going to be higher than you expect, sometimes it's going to be lower than you expect, and because we've got a spacecraft hurtling through at 1 kilometer a second, 400,000 kilometers away, it's shaking, we're trying to track it in real time. As Jackie said, maybe a water drop gets in the way. It's never going to be nice and neat. So you can start to see where on-off keying isn't a good move for our free space communications, because you're going to end up with these ambiguous cases where you're not sure if it's a 1 or a 0. So if you look at this second pulse here, right at the beginning, is that a 1 or is it a 0? It's about halfway in between. You can't put a 0.5 into binary. What do we do? But if we look just a little bit before it, we can suddenly see, well, it's probably going to be a 1, right? Because the power increase is really quick. And this is an important part of signal processing. Looking for changes in power is a lot easier than reading the absolute power itself. So that's the fact that we exploit in the coding mechanism we actually used, which is pulse position modulation. So instead of reading what the actual power is, we just look for when the power changes, and that's how we encode our information. Now, the way pulse position modulation works, I like to say it's a bit like rock and roll. So in rock and roll, we split our time into bars, and each bar has 4 beats. The 4x4 beat. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. We've all heard it, right? Now, pulse position modulation, which we use in the Artemis mission, does the same thing, but it introduces one extra rule. In PPM, you're only allowed to play a note on 1 beat per bar. So if I clap out this pulse position modulation signal like this, it will go something like this. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2. So you can start to see how we can encode information into the timing of our notes. So we can break our time into bars, and depending on which note in that bar we play, we can get a number between 1 and 4. And this is how we can cram information into our laser beam. Now, pulse position modulation is really nice for a few reasons. Like I said before, us on the receive side, we like it because all we're looking for is a change in timing. And this is why we needed that picosecond precision in our superconducting nanowire detectors. Because the more accurate we can tell when a photon arrives, the faster we can make these pulses, because we're just looking for when the photons arrive. But on the transmit side for the spacecraft, they really like it as well, because the laser spends most of its time switched off. So in spacecraft, they're trying to save every watt of power they can, because all they've got is those 4 little solar panels and the batteries on board. So they're trying to save power wherever they can. So a communication system where the laser is off for 75% of the time works great for them. So once we've decoded our pulse position modulation, we get our numbers between 1 and 4. We can run that through the CPU, some FPGAs and crazy electronics. And out the end, we get regular old internet. Our modem's got a couple Ethernet cables on the back. We can plug those Ethernet cables into the wall, and then that goes through the World Wide Web, where it lands in Houston Mission Control, where they received the internet frames and decrypted it and streamed it to YouTube. Now, there's one more part of the system I haven't talked about yet, and that is what we bolted to the back of the telescope. So the keen-eyed amongst you might have already noticed this box that we attached to the telescope. Now, what these are 4 10-watt lasers that we point back at the spacecraft. Because as I keep saying, it is really far away from Earth. It's 400,000 kilometers away, and the laser beam itself is only about 100 meters wide by the time it reaches us. So they can't just point at Australia or even at Canberra. It needs to hit Mount Stromlo specifically. So we use the lasers as a lighthouse, so they know where to point. These are actually 4 telescopes, because they need to work in both directions. So we're shooting the lasers out of the telescopes. It's kind of like looking in a telescope backwards. So it takes a small laser beam and makes it nice and wide, which makes it easier for us to hit the target. You also might be wondering why we used 4 10-watt lasers. Why not just make one big 40-watt laser and put that on the back? And that's actually because between us and the spacecraft, there's about 20 kilometers of air. Now, I like air, I like breathing, and I'm sure you do too. But from communication perspective, it's kind of annoying because the turbulence can cause our beams to do all sorts of crazy things. The beam can get wider, it can shift off target, it can fade entirely. So by using 4 independent lasers and splitting them up, we can be sure that each laser is going to pass through an independent patch of atmosphere, and at least one of them is going to hit the target eventually. This is called spatial diversity. Now, the really crazy thing in getting this system to work is we now have to steer 4 independent lasers and hit a spacecraft 400,000 kilometers away, moving at a kilometer a second. And also, the telescopes need to work in both directions because we need to be able to see the spacecraft. So light needs to be able to go through the telescope and hit the camera. And we also need to be able to steer the laser beam. So we have fast steering mirrors, which are robotic mirrors that we use for doing fine adjustment. And all 4 telescopes needed to independently track the spacecraft while the big telescope was also tracking it. So this was a bit of a challenge to design. One thing that we did do to make our life slightly easier, at least during the mission, was the telescopes on top had a variable divergence. So we could make the beam wider while we were looking for our target. And then once the spacecraft could report it back that it could see some flashing, we narrowed the beam and we slowly spiraled the beams in while we locked on. And at the end of it, we had, I thought I had one more system. Anyway, at the end of all that, we have internet. The Orion space capsule knows where to point its laser beam, and we can turn that laser beam into internet. And I'm going to pass it back to Jackie to talk about some of the results.
All right. Thank you very much, Cameron. So, overall, the demonstration was a resounding success. As we mentioned earlier, there was a live stream on YouTube that anyone could watch, and you can even still go back and watch now. You can routinely see it swapping back between the low definition of the radio frequency and the high definition of the optical, and it basically worked a complete treat. So we weren't sending any critical data over the optical communications link. The technology isn't quite ready for that, but this is definitely the first step in proving that it's reliable enough to do actual scientific data next time we want to use it. So here in Canberra, we were able to downlink over 43 gigabytes of video footage over the course of the 10-day mission. And we were able to hit the maximum speed of the mascot terminal on the Orion capsule of 260 megabits per second. So a nice little bit of trivia as well is that during this mission, humankind went further from the Earth than they ever have before, including during the Apollo missions. And that very moment when everyone in the capsule crossed over the threshold was streamed back here, caught by the Quantum Optical Ground Station in high definition. That's my personal favorite result from the whole demonstration. I think it's really cool. So now that we've done Artemis II, what next? Well, we have a couple of directions we can take the technology. First of all, I kind of alluded to it earlier, we're looking into deep space optical communications. So how does the technology have to change and evolve when we want to go further than the moon? Well, earlier last year, we demonstrated optical communications capabilities with NASA's SPIE probe, which is heading out towards the also named Psyche asteroid. So it's equipped with an optical payload, and we were able to point it at the Anglo-Australian telescope, which is up in Siding Spring Observatory, and we were able to get light on our detector. That's what we were looking for. So we were very happy with that. We're also always interested in making this data transfer quicker. You know, it's kind of the key motivator that drove this technology in the first place over radio frequencies, that we can do much, much faster speeds. So we're always looking at ways where we can optimize the speed and make it faster and faster to service high-speed internet all around the world. And that's kind of where my research comes in. So in my PhD, I've got a couple of projects going on, one of which is looking at concepts for a relay network in cislunar space between the moon and the Earth. So the advantage of this is by having several satellites that are basically parked in between the moon and the Earth, what we can do is drastically reduce the requirements for size and weight and power of these satellites, all of which are huge constraining factors when we're making our satellites in the design phase. And in being able to have these smaller requirements, we can kind of put more advanced technologies like very cutting edge detectors, things like that, on these satellites without having to use a huge optic, for instance, which is typically the source of most of the weight and the size of these spacecraft. This kind of approach also enables very modern approaches to detecting the optical signal itself, such as coherent communications. Now, this gets a little bit tricky, but I will do my best to explain. Coherent communications encode extra information into the link by manipulating a special property of light known as its phase. And so this is something that's been done in the radio frequency industry for a very long time, and we're kind of trying to take this approach into optical now. As with most things we try to borrow from the radio frequency industry, turns out it's actually really difficult to do in optical, primarily because of the characteristics of the wavelength of light that we're dealing with. But the bright side is that coherent communications can massively improve the speed of the link itself. The downside is that it's very difficult to detect. The detectors that you need to use to run coherent communications are a lot more complicated, a lot more expensive, and a lot bulkier than your traditional pulse position modulation and on-off keying detectors that Cameron was describing earlier. And so doing this as well is also massively compromised by the Earth's atmosphere. As Cameron mentioned earlier, I love breathing, we all love breathing, but the phase of light specifically is majorly disrupted by the atmosphere. But there are some ways around it, and we are working on solutions. And I'm going to invite Cameron back up to talk about how we deal with that with adaptive optics.
So turbulence becomes a big problem for us in the high-speed coherent communications we're interested in, largely because we need much smaller fibers for this to work. That's just what you get when you're working with coherent light. And turbulence does all sorts of awful things to your laser beam. So this is a demo I've borrowed from my friends over at Durham University, where they've shone a laser through a fish tank, and you can see the beam quality quite nicely. Then they switched on the pump, and you can see it does all sorts of awful things to the beam quality. This causes problems for us because you can't cram this into an optic fiber anymore. So we need some way of compensating for all this atmospheric movement. Now, thankfully for us, unfortunately for them, the astronomers have been dealing with this for about 30 odd years. And this is why we're up at Mount Stromlo, because they work with systems known as adaptive optics. What this is, in short, is we need a system to measure the turbulence, a wavefront sensor, and a system to correct for the turbulence, a wavefront corrector, and a controller to sit in the middle and apply all these corrections at about 1,000 corrections a second. And these systems have been in place since the 90s for astronomy instruments. And I got a great image here from the European Space Agency that they took of Neptune out of the very large telescope in Chile. So this is a ground telescope, it's not Hubble or anything, and as a result, you kind of just get a blue smudge. But they switched on the adaptive optics, and suddenly you can see all the clouds, and it makes the image you get nice and crisp. So the hope for the next generation of free space laser communications is to see how much of this technology we can steal for the astronomers and make it work in laser comms systems. And this is where my research comes in, because not only am I trying to steal from the astronomers, I'm also trying to steal from the telecom industry. Because the telecommunications people have already spent 30 years and billions of dollars on research and development trying to see how much they can cram into optic fiber. So this is great. It lets us get systems which have got remarkable economies of scale because they've already linked every computer in the world with optic fiber. You can build these systems reliably, repeatably, with great power efficiency. It's great. We want to steal as much of that technology as possible. So the system I work on is called the Coupled Optical Waveguide Wavefront Sensor, or COWS, as I've been calling it. And it's a specialty optic fiber. It's about 0.2 millimeters across, so it's about twice the width of one of your hairs. And it has 126 little cores in it, so corelets, I've been calling them. And what happens when you put this fiber in the focus of a telescope is as the atmosphere goes across, these little corelets, they're going to start to twinkle. And I've been working on an algorithm to measure this twinkling and reconstruct the turbulence which caused it, which means we can send commands to our wavefront corrector and correct for the turbulence. And the hope is we can, by borrowing this photonic technology, we can build systems cheaper and build a lot of them so it can fill out the whole planet and get 24-hour uptime. The other cool area of research we're really interested in is in quantum applications. So you might have heard a lot of noise being made recently about quantum computing. Some of the big headline results was Microsoft announced their first quantum CPU last year with Majorana 1, and they announced version 2 of Majorana 2 this year. And a little bit closer to home, SPIE Quantum has been looking at building the world's first commercial quantum computer up in Queensland. Now, what these quantum computers do, they can solve problems which are just fundamentally impossible to solve with a regular computer. Even if we broke into Sam Altman's house and stole all the GPUs from ChatGPT, you still can't solve the sorts of problems that even a small quantum computer can solve. So all this excitement has got people wondering about what a quantum internet will look like. How can we connect these quantum computers to each other in the same way we connect a regular computer with each other? And this leads to the obvious answer. Why don't we just copy the regular internet? Why don't we just connect our quantum computers with optic fiber the same way we connect every other computer with optic fiber? Now, the problem with using optic fibers for quantum communication is it's somewhere between difficult and impossible. Because a corollary of the Heisenberg uncertainty principle says that you can't amplify a quantum bit or a qubit. If you try and amplify any quantum information, it's going to collapse the quantum state and you lose all that quantum info. So instead of putting optical amplifiers every 100 kilometers like we do in a regular communication network, you need to put quantum repeater nodes instead. And these are functionally just small quantum computers. So if you wanted to connect one of the quantum experiments down in the lab over there to Michelle Simmons' quantum computer up at UNSW in Sydney, you'll need 3 or 4, maybe 5 quantum repeater nodes in between us along the Hume Highway. So this doesn't scale nicely. It gets really expensive really quickly. And this is somewhere where free space optical communications actually might let us get a little bit cheaper. Because if instead we beam our quantum bits up to a satellite, we can use one repeater node. We can hold the qubits up on a satellite and then beam it back down to our second quantum computer later. I realize this sounds crazy, but there are demonstrations which have already proven you can get kilobit per second links. So pretty slow, but we have done it. There have been research out of both China and Japan have got satellites which can do this. What we're doing at Mount Stromlo is trying to do it quickly. And where I can talk about the next cool, exciting project we're working on, where we are setting up a 10.5 kilometer link between us at Mount Stromlo and the roof of this very building. We're going to be doing continuous variable quantum key distribution, which means we are encoding quantum information into the frequency of the light itself and shooting it out of a laser terminal, which we've crammed inside a shipping container in Mount Stromlo, across that 10.5 kilometers to the roof of this building. So if you see people climbing around the roof in the next few months, that's what we're doing. Now, this has immediate applications for defense. Quantum key distribution is really cool because it means it's a unbreakable encryption, not a really hard to break encryption that you need 1 billion years or something to solve. No, it's unbreakable. So it's cool from that perspective. But it's also a really important stepping stone on the way to a quantum internet. Because if we can do quantum key distribution, that opens the way for encoding arbitrary quantum information to hopefully link more complex quantum instruments. And with that, I'm going to play a video to close out and invite Jackie up. Do I need to press the button? Oh, gosh. Now I'm going to play a video and invite Jackie up to close out the talk. I think that was technically meant to be background music or something, but...
All right. So yes, the demonstration with Artemis II was, as I said earlier, a resounding success. Pretty much everything, every milestone we wanted to hit was achieved, and we did everything basically without a hitch. So again, I'd like to acknowledge the very, very talented team of optical engineers up at Mount Stromlo, the entire research team we work with, as well as the countless individuals from NASA who flew out here multiple times to help us troubleshoot our own systems. And so, next time you're up there on the moon, watching the season finale of Euphoria in stunning HD, you will know that there's a laser coming your way from us to keep your connection nice and smooth. Thank you very much, everyone.